Hello and welcome to Corecast. I am your host, Tim.
And I'm Sahil. Welcome everybody to a brand new exciting episode of Quirkcast. And a few logistical things. If you haven't already, do join our Discord channel. And if you're watching on YouTube, where we do this every Tuesday, 5 p.m. Pacific, 8 p.m. Eastern, do ask us questions during the episode, and we'll get to them. So without further ado, let's get to it. So Tim, we this is basically a part two of our last episode we recorded. So for anyone interested, do check that out. We set up like a lot of groundwork for this episode regarding information and physics. But I wanted to get to the crux of this episode and then like work backwards. So this episode's about what we call the black hole information paradox. Could you give, at least at a high level, Tim, like what's intriguing about this paradox? Like why is it a paradox? And you can describe it at a high level, and then start defining terms as we go through the episode.
Yeah, so the crux of this problem is that we have two theories, one quantum physics and the other Einstein's theory of relativity. Both seems to be describing nature. However, in certain situations, in extreme situations, in particular black holes, the predictions from these two theories come to a head-on collision. On the one hand, quantum physics says that information has to be preserved. And so it means that even though black hole is very good at deleting stuff, the information has to persevere. On the other hand, Einstein's theory of relativity says that there's a cosmic speed limit, and if things get stuck in a black hole, there really is no way to retrieve it. So Einstein's theory seems to suggest that information somehow is gone. And when you combine the two, if you try to reconcile that, you will come to another issue and this is something we alluded to last time, the question of whether space-time is smooth or not. And these two facts we'll learn that they're intimately related. So whether information is preserved or not, that also leads to the question of whether space and time is smooth or not. And this is a conundrum that physicists have been dealing with for the past few decades now.
Yeah, no, that sets it up well. So what you're saying is that quantum mechanics, there's this quantity called information that's preserved. But if you take like I guess, the general relativistic approach to black holes, and say you like throw an object in, it goes in, it can't come out, then you've lost that information. So it seems like these two things are at conflict. Is that at broad brushstrokes approximately what
Yes,
you're trying to get at?
exactly. Exactly.
Okay. Great. So why don't we start and look at like can you just for the audience, I know several of the audience members may be familiar with this, but for any new audience members coming in, could you just briefly define what information is in the context of this conversation?
The information is it's similar to in physics we learn a lot about energy, the conservation of energy, right? Like you can use energy to do things. To move a car, you can use energy to heat up the stove, and we learn in physics that information can neither be destroyed or it's also created, right? Like the reason you can heat up your stove is because electricity comes from the power lines, come to your house, and you heat it up. Um, and it turns out that there is a similar notion, and in fact, it's more sacred, of information. And information in quantum physics has to do with possibility, right? Like if I have a particle, this particle is able to interact. This particle can be up here or down here, right? So the fact that this particle can do things, it's kind of linked to the existence of this particle, right? Even if I destroy these particles, I should be able to keep track of what it became, right? Like a particle maybe can decay into two other particles. I can keep track of that. Um, so in quantum physics, there's this notion that you can always keep track of stuff. You can always follow the lineage of something, and and
Mhm.
and, and that something can be formalized into this idea of information. It's the possibility of doing things. Right? In fact, it's even more basic than energy. Forget about energy. Even just me moving in space and time, maybe that doesn't take any energy. Like things are changing. Like I can keep track of my hand, the particles in my hand moving. So so this fact alone, it's sort of linked to just existence itself, right? And in quantum physics, the most sacred law is that this property of stuff is preserved.
I see. I see. You also aptly characterize it as like possibilities. So you can think information as possibilities. Is that also correct?
Yeah, I think that is also correct because quantum physics ultimately is not deterministic, right?
Mhm,
So you can have, let's say my hand is a particle, right? In the
mhm,
quantum mechanical realm, my hand might jump to the left or jump to the right, but let's say 50-50, right? It has to do one of
mhm.
those things. If I jump to the right, the least I can say is that, hey, look, I have to had started with some hand in order to see a hand jumping to the right, right? Like, I have to be able to keep track of it. We can't just have like a hand appearing out of nowhere with nothing preceding it. So some things
Mhm.
gotta precede it, basically.
Mm. Okay, so that makes sense for information, and for listeners who are more interested in getting into the weeds on that conversation, we have a bunch of past episodes on that, so do check those out. Now, Tim, I want to also touch upon black holes. So people, I think, generally know the notion of a black hole, like it just goes around sucking things in, and can we sort of talk about maybe the more non-trivial things about black holes that people wouldn't necessarily know from, like, if they had only exposure to like pop science type of stuff.
Yeah, I would say one of the biggest misconceptions about black hole is that black hole is actually not an object. Black hole is not like a thing you can hold in your hand. I don't know if you're a Thanos or whatever. It's not like you can just grab a black hole and do something with it, right?
Uh-huh.
Black hole is actually a region of space. If you have seen, I don't know, like Doctor Who or some of the sci-fi movies, it's black hole is like a portal. It's like a region of space where you can enter. But the interesting bit is that once you enter, you cannot escape, right? And also, what's interesting is also that imagine you throw something toward the black hole. Let's say you do a calculation. You be like, oh, I throw my laptop into the black hole. I can calculate that for sure it's gonna go into the black hole. You actually
Mhm.
never see it fall in because the signal from the laptop, let's say the light or from the screen, at some point once it passes the point of no return, that signal can't even reach me anymore. So I'll never know that my laptop has fallen into the black hole. There's a really interesting place in the cosmos, and we also know that they exist. We have taken pictures of them, so these things are there. And there's also this really interesting boundary, right? Or at least an apparent boundary where a point of no return. But one thing to keep in mind is that this boundary actually is artificial. At least we believe it to be so, because the moment you say, hey, I don't believe this boundary is true, you yourself can choose to fall into the black hole. And we know that from physics, as you fall into the black hole, you the point of no return, actually you can't feel very much. At least if Einstein's theory was correct, you would just feel like, oh, I'm just kind of floating around in space. You actually wouldn't feel like all of a sudden you've crossed the boundary of no return. So these are some of the facts that I would say are not maybe as commonly understood.
Mhm. I think for the purposes of this discussion, can you walk us through a scenario where, like, say I'm on the outside and I like throw something towards the black hole, or you see somebody go towards the black hole? What what do you see as like an observer from the outside? Let's say you're in a spaceship that's like a safe distance away, and then one of your buddies decides to just say, hey, I'm gonna go into the black hole. Like, so what do you see?
What you actually see is actually that, and in relativity, there's an effect, time and space dilation. Basically, space and time will stretch, right?
Hmm.
So for those who have seen Interstellar, you might get like a little taste of that. It's a great movie in terms of physics that I like. But imagine as you're falling toward the black hole, your time relative to people outside will actually change, right? And imagine if you're trying to send signal, let's say your heartbeat outside, your heartbeat will slow down from an outside observer. And at some point, let's say imagine Sahil, you decided to go toward the black hole, and I'm just like hanging
Hmm.
out on the edge. At some point,
Hmm.
your heartbeat is going to slow down more, and more and more, and also the signal will get weakened and weakened. It's gonna redshift, basically. It's gonna slow down, and if you really do decide to fall in, for my reality, you never succeed in falling in because the amount of time your heartbeat will get stretched so long, it will be as if you get stuck on the surface for eternity. But but
Mhm.
but let's say you have a beam of light. You're trying to shine at me. Be like, hey Tim, look at me. I'm still alive. That beam of light, that signal will get weaker and weaker and weaker. They'll be red shifted. It'll be harder and harder to detect until eventually, like no instrument that I have will be able to detect them. So kind of Sahil, from my perspective, you will seem like fading away from
Mhm.
existence, but I will never see you
Mhm.
fall into the black hole.
Okay. So let me get this straight. So if I decide to go towards a black hole, as you're seeing me, you'll see the photons coming from me having longer and longer wavelength, i.e., red shifting, meaning the photons will get redder and redder, meaning I will appear redder and redder, and eventually you'll see me like slowly and just it will take an infinite amount of time for you to see me like go not necessarily into the black hole, but maybe like just at that boundary of like that point of no
Mm.
return. Is that fair to say?
Yes, yes, that's true. And the funny thing is, if at any moment I decide that, hey, look, Sahil, you're my best buddy. I miss you. Like I don't want
Mhm.
to see you stuck on the horizon. The point of no return is called horizon. I could myself decide to fall chase after you and fall into the black hole.
Mhm.
And the moment I cross through the event horizon myself,
Mhm.
I will start to maybe see some of your signals again. I will see what happened to you finally. Right?
Mhm.
So even though you kind of become stuck on the surface and kind of your existence fade away, I could decide to recover that if I myself choose to go into the black hole.
Mm. I see. I see. Okay, that makes sense. So so then from this now taking a step back, we're looking at this black hole information paradox, and my question is that one side things go into the black hole, they don't come out, and then and then that information is lost on one hand, and then the other hand there's quantum mechanics that says that information is preserved. So why can't the resolution of this paradox simply just be that from an outside observer you never see anything go into the black hole? So like isn't that a case shut with this? So then like nothing ever falls into a black hole from an outsider perspective.
Yeah,
Nothing's actually lost.
in fact, that's what physicists thought about, and people thought that that wasn't a problem, like Leonard Susskind and others. Yeah, they imagined that even 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 information is relative. What, what what they were thinking about, and what you describe is called complementarity. Um, it
Mhm.
means that there might be two reality describing the same situation. Like for example, for me on the outside, if I never decide to go into the black hole, Sahil, you are stuck on the surface. To me, the inside of the black hole might as well not exist. Right? All the information is still preserved. All the stuff that you brought with you is I because I never see you fall in. Right? It's everything that technically kind of falls in. I never see it fall in. So maybe from my perspective, they didn't fall in, right? So all the information is still plastered on that point of no return, right? But the moment I
Mhm.
decide to say, hey, look, I don't like that. I personally decide to fall into the black hole. The moment I cross that boundary, I will start to see these information in front of me. There's a slightly different reality, but that's okay because I can never go back out. I can never be like, hey, Sahil, guess what? I'm gonna go in with the black hole with you, and I'm gonna come out and
Mhm.
be like, hey, look, there's a contradiction. I can't do that. So
Mhm.
physicists thought that the in an absolute sense, information is preserved, but where the
Mhm.
information is might be relative, right? Depending on whether you are on the outside of the black hole or you decide to fall in with it. So people thought that this is the entire thing now. Okay, there's complementarity and there's no problem.
Hmm. I guess then is this an open and shut case? Are we done? Did we solve
No,
this on this podcast?
there's an extra problem, and
Oh,
that problem is coming from Hawking radiation.
okay. Well, why don't we describe what Hawking radiation is? Like, yeah, like what is this Hawking radiation?
So yeah, so while the math is complicated, the crux is simple. Quantum physics tends to wreak havoc on things. Things that this is just a general principle with quantum physics. Kind of all the things that could happen, with quantum physics has the possibility of happening, right? So
Hmm.
loosely speaking, is that in the vacuum, things could fluctuate out. Like particles can get created and destroyed, right? And what
Hmm.
happens is particles and antiparticles they could get created. But if they get created at the border in the black hole, one of them could fall into the black hole, and one of them could escape, right?
Hmm.
And keep in mind, the math is complicated. This is kind of like a physical picture, a very intuitive
Hmm.
physical picture to view. It means that on average, this will happen, I don't know, once in many years. It actually takes a long time, right?
Hmm.
But what happens is, well, it means that, randomly, the black hole can radiate stuff away.
Hmm.
And because energy, even though it's not completely conserved, it still has to conserve to some extent to this scenario. That means the black hole will shrink. So slowly but surely, the black hole
Hmm.
will emit these radiation, and these radiation will just
Hmm.
escape very, very far away
Hmm.
near the surface of the black hole, and the black hole will shrink and shrink and shrink and shrink, and eventually totally evaporate, just gone, completely gone, right?
Hmm.
And that throws a wrench to this complementarity argument because if you believe that, well, whatever information that was stuck on the black hole, well, when the black hole is gone, there's no more, right? So where did they go?
Hmm. What before actually one question I have before we continue down this train of thought is like you mentioned at the surface there's this particle anti-particle pair. At least that's a visualization of like how it happens. And then one particle goes into the black hole, the other one goes out, and you say it loses energy. But like I thought if two particles get created and one goes into the black hole and the other one escapes, like why does it reduce in size? Like why not just stay the same size?
Yeah, I mean the details, the physics is unclear. Probably involves quantum gravity.
Hmm.
But if you just combine quantum physics and relativity, you know that the curvature of the space time. I mean these particles popping in and out is from the fact that space time is curved. And because space
Hmm.
time is made of, if we believe quantum physics is real, space time should be made of quantum stuff. So the curvature
Hmm.
has some kind of energy associated with it. So
Okay.
that energy will leak a little bit. So you can
Okay.
also think of
Oh,
it as the leakage of the energy in the gravity, so
mm,
that black holes glow.
okay. And then is this like a radiation like the sun kind of like radiation, or is this even like less? Is this just like how yeah, give me a sense of scale with this.
I think it's way dimmer. I think it will
Mm,
take like trillions and trillions, trillions, like I don't know, like 10 to the 10 times the age of the universe for like a normal black hole to evaporate halfway. Something like that. Don't quote me on the numbers, but it takes a heck of a long time. Like the temperature is
mm,
really, really low. But slowly and steadily it does happen. It's a very, very slow process. Nothing like a star. It's not even like your coffee. Your coffee will glow radiation because it's hot. But black hole is this is pretty weak radiation.
mm. Okay, so it emits this really weak radiation, and we just want to clarify to the audience members that general relativity does not predict this, correct? Like it
Yeah,
does not predict a black hole radiance.
you have to combine relativity and quantum physics. Quantum physics has to go in, and then you see, lo and behold, holes radiate.
Okay. Okay. So it radiates, and as it radiates, it shrinks in size at this just unimaginably slow rate. And then okay, then okay, so it radiates away, and I assume it radiates away information about the black hole as as like photons or whatever particles are radiating out. And then how does that again lead to the paradox?
Yeah, so basically, it's a conflict of two realities, right? Like
Okay.
imagine I'm on the outside, and Sahil, you decide to go into the black hole, and let's say I survive
Hmm.
for a very very long time, and I see that, hey Sahil, you were stuck on the black hole, but slowly the black hole evaporates. And from my point of view, your truth, your information, kind of got splattered out all over the cosmos. Because the radiation, let's say, it's relatively uniform. It's everywhere. Like
Hmm.
Sahil, I don't know, your hair, your eyes. One went to the left, one went to the right, one went to Andromeda, one, I don't know. It's all over the place. And to me, it's quite sad. Sahil, you're really like gone. So that's one reality, right? But the other reality is like, hey, you know what, Sahil? You're my best buddy. I'm gonna follow you. I will go to the black hole with you, right?
Okay.
Imagine I go in with you. If I go into the black hole, you're with me. Like I don't see any radiation. Like Sahil, you're with me, right? So
Yeah.
in that reality, you're not plastered all over the universe. You're just you,
Mhm.
right? So the question is, well, where the heck is in where the heck is the information? Is it really all over the universe, or is it like where the black hole is?
Oh, so you're not even sure exactly where the information is to begin with. I mean, before, if you didn't consider radiation, then the information would be somewhere on the surface. It could be plastered all over the surface, but it'd be there basically.
Yeah, so there's this thing called the holographic principle. Like we could believe that,
Hmm.
hey, look, whatever happens to the inside of the black hole might just be like maybe you might be able to reconstruct it from what's going on the surface. So that's not crazy, right? But now, like, hey, Sahil, you are all over the universe, left and right, left, right, up, down, front, back, right? But if I
Hmm.
choose to fall into the black hole with you, you're there. Well, are you there or are you all over the cosmos?
Hmm. I see. So complementarity no longer holds, or has that been violated, or like?
Well, it's actually a little more subtle than that. Um,
Okay.
so physicists, if you really buy into complementarity, which I would, um, then you will argue that the information is let's take this logic to the extreme. You say that, well,
Okay.
Sahil, your information are both all over the cosmos, because the
Hmm.
radiation, and also in the black hole, right? If
Okay.
you take complementarity to the extreme, both are true, right? In order for both of them to be true, um, in quantum physics, there needs to be this thing called entanglement. Why is that?
Okay.
Because quantum physics tells you that information can neither be destroyed or created. It's conserved. It
Hmm.
means that I can't destroy it or I can't create it either. So, in order for information to be both in where the black hole is and really far away, there needs to be a link between them, basically. In order for me to have a link between them, they need to be what we call entangled, like redundant in some ways, right?
Hmm.
So if you take the complementarity to the extreme, it means that, hey, there's going to be a lot of what we call entanglement between where the black hole is and
Hmm.
where really far away in the cosmos.
Hmm. Okay, so entanglement we've talked about several times. I just want to see if I can like I guess give a concise description. It's essentially can you think of it as like this correlation between maybe two different regions of space where like particles are and they're entangled with each other, so they're like correlated with each other. Is that one way to think about it?
Yeah, I think yeah, it's a good way to think about it. But I think there's a
Mhm.
better, more modern way of think about it.
Okay.
If we take the analogies that space time is a fabric, you can ask, well, if I look at a piece of cloth, right? If I look at the
Hmm.
fabric, you see like these crisscrosses, from
Hmm.
yarn or whatever, right?
Yeah.
Um, you know, for all this analogy, you can say, well, space time is a fabric. When I zoom in, what is the crisscross? What is it made of? A modern way to view it,
Mm.
that crisscrossing, the fabric, the little bits and pieces, that's entanglement, you know.
Mm.
And if we follow our previous episode, what does it mean when I move my hand in space-time, right? From here to there, you know.
Hmm.
It's like the particle is following the yarn of the space-time. There's a register on how many particles here, and it follows the entanglement to go from one to the next. There's a correlation, right, from one point to the next. So this is the modern way to view about it. Entanglement is what weaves the space time.
Mm. So just to kind of take this, kind of ask the converse question, if there was no entanglement between particles, then you wouldn't be able to move your hand through. There'd be like no real way to move things through space and time. Is that fair to say?
Yeah, so this comes to the next point, right? If entanglement is cut at some point, you know,
Hmm.
that means there's gotta be a great, like an obstacle. And this is what we call a firewall. Because you cannot
Hmm.
predict what's gonna happen right in front of you. It's like driving a
Hmm.
car and just heading into nothing, right? And all scrambled up, It's
Hmm.
pretty much driving to like a head-on wall, basically.
Hmm. Hmm. And this is even worse than like a normal wall, because normal wall is like even that is entangled with the environment. But here's just a true like nobody knows what's gonna happen once you like go through that.
Yeah, I mean it's terrible. Like I mean for people who know about coding, right? Like if you
Yeah.
do coding, if you just look at some random points in your memory, it's just
Mm.
random numbers, and the random numbers could be 1 trillion, negative
Mm.
bajillion. But you can't predict it, and when it's all scrambled up to you, it would just look like a firewall of death, right? Because as you walk through it, you will be scrambled up yourself.
Oh, so it won't be. Would you say it won't be coherent? Is that a mild way
Yeah,
of putting it?
that's a good way to think about it. Yeah, it's almost like you're going into a blender, a quantum blender, just blend up all the stuff
Oh,
that you have.
that that does not sound pleasant at all.
It is not pleasant, indeed. That is not pleasant.
Yeah. Okay. So we talked about. Okay. So if you have a disconnect, like if let's say two regions of space at some boundary are have this like disconnect that they're not entangled with each other at all, then you have essentially what you described as a firewall, meaning like some sort of scrambling. So actually, I want to quickly ask a little bit more of a nuanced question on this. Say you had two sides that were like entangled with each other, in their own ways, and you were on one side, and then there was this like part of space, like this very thin slice of space that where it was these two regions are not entangled to each other. Would that still be considered a firewall where you would just get scrambled up?
Yeah, I think that would be. I mean, if there's
Mm,
no entanglement, you wouldn't
mm.
even call this part of space next to each other because you wouldn't be able to go from one place to another. Because if there's no correlation, you cannot influence the other side.
Oh, okay, okay. And so, like, okay, I guess, all right, that makes sense. So now we've described what a firewall is and how deeply unpleasant it sounds at like a philosophical level and even a physical level. Where does this come in with the black hole information paradox?
Right. So
Yeah.
yeah. So this is the math is very technical, but I think we can loosely explains this
Mhm.
using analogy, right? Because when we say you have let's say we follow this complementarity logic, it means that there's two reality.
Sure.
One reality is Sahil in the black hole, the
Hmm.
information is there, and the other is the reality of Hawking radiation all over the cosmos. The only
Yeah.
way for that to be consistent is that there needs to be entanglement. Just imagine
Hmm.
like a spaghetti. There's a lot of spaghetti entanglement linking where Sahil should be
Hmm.
and the Hawking radiation. But keep in mind that there's also in quantum physics there's actually a maximum amount of entanglement. Like it cannot blow up that much, right? So at roughly, if you do the calculation at roughly halfway through the evaporation process,
Hmm.
you'll see that the black hole is basically packed with this entanglement spaghetti as much as possible.
Hmm.
There's no more. You cannot pack more, right?
Hmm.
So that means in order for the black hole to Hawking evaporate more, something's gotta give. Because it cannot pack more spaghetti of entanglement in there. You can't. There's no more that can be packed in, right?
Hmm.
So we don't actually know what happens then.
Okay, I just want to make sure I understand this. Taking a few steps back. So, okay, okay. When you talk about packing it with entanglement, I want to just understand that a little bit more. So, you have a black hole, which we can imagine is like a sphere, and you mentioned like half of it, maybe like a half of the outer shell of it, um, is packed with entanglement, and the other half is like, don't know what's going on with that. Well, I'm trying to understand like what do you mean by packed with entanglement? Like what? Yeah, I just can you explain that a bit more?
Yeah, and I guess just you can just kind of imagine a sphere, right? So
Okay.
every part uniformly on the sphere, like imagine the sphere has some pixel, right? You can kind of roughly
Yeah.
imagine it.
Hmm.
As you Hawking radiate, I don't know, a random dot on the sphere might be entangled with that Hawking radiation. Maybe one dot to the left is linked to a Hawking radiation to the right.
Hmm.
And as more and more happen, it's almost like there's this big spheres with like threads, a little thread coming out, you know,
Hmm.
connecting it to the Hawking radiation, right?
Hmm.
So as time goes on, there's more and more of these threads, right?
Okay.
So now this black hole is filled with threads, you know.
Hmm.
But it turns out there's a maximum amount of threads that the black hole can contain, because
Hmm.
it's reasonable. Because like, look, the event horizon has a certain area. You can't
Hmm.
pack that many threads in it. Yeah? So if
Hmm.
Hawking radiation demands that you have to create a new thread,
Hmm.
when the space for threads are maxed out, it's maximally entangled, what we called.
Hmm.
What happens now? Is the Hawking radiation going to stop, or is it going to keep going?
Mm. So one, okay, so just to kind of make sure I really understand this, are you saying like, could this be the analogy be like, if we imagine all the information's on the surface of a black hole, it gets radiated away, and because there's more I don't even know how to really describe it. I mean, I'm just using the sphere analogy here, but maybe nobody knows what goes on the interior of a black hole. It could be vastly different. But just say we go with the sphere analogy. You have a sphere, and then all the information is on the surface of a black hole. There's more like volume than there is like area, loosely speaking. Like if I were to take like, points of a certain size and map them onto like the area, there'd be more volume. And so are you saying like because of that constraint, you can't like entangle everything? Is that a fair way to think about it? Or
Yeah, well, the fair way to think about it, because when Hawking radiation leaks out, the universe is
yeah.
super large, right? That's the space
Hmm.
outside of the black hole is so much larger than the
Yeah.
black hole itself. The black hole is just a sphere,
Yes.
you know.
Hmm.
So there's so much more possibility outside than inside,
Okay.
right? So as you radiate Hawking information, as you radiate Hawking radiation, the bits of information from the black hole slowly leak out to a really large space. But at some point, like at some point, basically the black hole cannot accommodate more of the entanglement anymore, because the outside is so much larger. The outside is basically infinite, right? So at some point it's
Oh,
gonna hit an upper bound, basically.
oh, I see. Eh, Then why can't it? Okay, I guess naively, why can't it? If the space is so much larger, what's stopping like the entire black hole from being entangled? Like maybe like a portion of this so-called infinite space. Why is there like what is causing the limit of the black hole to have its information entangled with like the rest of space? It's not like that half portion is covering all of the space.
Right.
There's like all this other stuff. So I'm wondering like why does it stop at half? I mean, I
I,
understand the math can be very involved, but like is there an intuitive way to think about like where this limit is? Like why is
yeah.
there even a limit?
Let me just add, it's not exactly halfway. It's just somewhere in between, right? It's somewhere in
Okay.
between no evaporation and completely gone. As
Okay.
as the black hole shrinks, its capacity for entanglement also is shrinking. But then if the
Mm,
information is not leaving, you're gonna get
mhm,
more and more entanglement. So at some point it's gonna hit a max, because the capacity for the black hole is shrinking too, because black hole is getting smaller, right? So its capacity maintain those correlation entanglement, it's also shrinking. So at some point, there's the balance. At some point, somewhere halfway, it's not exactly halfway, you reach
Mhm.
maximum entanglement. There's no more. It cannot. It's at capacity. So so a naive expectation is that it cannot Hawking radiate anymore. You are kind of stuck, but still Hawking radiation still needs to keep going. So we don't
Mhm.
actually quite know exactly what happens.
I see, I see. Okay, so as it radiates away, I can think of it like spaghetti is like coming out of the black hole, loosely speaking, in terms of this Hawking radiation. And spaghetti you can think of as entanglement. And you reach a certain point where like you've reached the map. There's a certain amount of spaghetti you can pack into a black hole. And as it Hawking radiates away, these strands go out, and then you reach a certain point where you have this maximal amount of strands based on the size of it. Is that
Exactly,
is that right?
exactly. Yeah, exactly. So at
Okay.
some point you have to reach a maximum capacity, unless if some of the spaghetti gets cut, right?
Okay.
But when you cut it up, it means that you've erased entanglement. That means you've
Mhm.
deleted a correlation between space-time. That means you created a little bit of a barrier between the outside and the inside of the black hole. So this is the firewall paradox, basically. It
Mhm.
says that in order for the black hole to radiate some more, to do more Hawking radiation, you, the black hole has to get a haircut. I mean, it's got too much hair coming out. It's got to have a haircut. And when you cut those hair, there's going to be a massive amount of energy, right? And
Mhm.
Einstein's theory doesn't predict it. In quantum physics, we don't know how that happens. But some physicists, this lead to some physicists to believe that, hey, there's something more than quantum physics and Einstein's theory. At
Mhm.
some point in the black hole's life, the hair's got to it's got to get a haircut, basically.
Okay. So what you're saying is when a black hole Hawking radiates, there has to be entanglement. That's like a given. And when it reaches a certain, would you say maximally entangled state for the black hole, meaning like the maximum number of, spaghetti strands coming out? And then in order for it to, if it were to Hawking radiate more, it needs to basically cut these strands, meaning that information is lost now. And so then it can continue to Hawking radiate and get smaller and smaller and smaller.
Yeah, exactly, exactly. It's like I got too
Oh.
much hair on my head. I don't even have any pore for any hair to grow out. But if quantum physics is right, the hair still keeps growing. Hawking radiation keeps happening. So
Mhm.
So the only way to fix this is there's got to be some haircut procedure. I don't know what's cutting the hair. We don't know. But
Mhm.
physicists believe that there's a haircut happening. It may be
Mhm.
happening randomly. But when a haircut happens, there firewall. We expect a hot firewall to emerge that surrounds the black hole, right?
Oh, does okay, then oh wow. So if any of these hairs get cut, then you would expect because now that those regions of space would be like not entangled with each other anymore.
Exactly. This has to do with error correction a little bit. So
Mhm.
physicists believe that if you cut one hair, you know, your almost like your hair got screwed up a little bit, but the error
Mhm.
correction will patch it up, so it doesn't look
Mhm.
too dramatic.
Mhm.
And then, but slowly but surely, you have more and more entanglement that gets cut. At some
Mhm.
point, even this correction couldn't save your haircut anymore. Then this black hole will become unrecognizable. Look, black holes are defined by a place in space where you can fall in, and it's got a place of no return, right?
Mhm.
If all of a sudden a black hole becomes a firewall, well, it's not a black hole anymore. You can't fall in there. If you try to go in there, you just get burned up, right? So black hole cease to
Mm.
become a black hole.
Ah. So does this even hold? Let's say the black hole is not at that point where the firewall appears and I fall into the black hole. Would I possibly also experience this firewall thing?
We don't
And
know.
this is speculative, super
Yeah.
speculative, but like coming from a very speculative perspective, what would you say?
It's not clear. If you buy that it's a firewall, let's say Sahil, you fall
Uh-huh.
into the black hole, and then at some
Yeah.
point, and then at some point the a firewall is created, then I would have reason to believe that Sahil, I think you are toast for
Oh,
real. So
so there's no way of recovering at all. Like once you go through the firewall, it's over.
well, there might still be two realities, right? Because
Mm,
the linkage between what's inside the black hole and what's outside is severed now. There's no,
mm,
imagine there's some process that severs that. So maybe 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 Sahil, you will lead your life in some ways. I don't know how you carry out your life. Maybe in some weird way you will still exist, right? But then you're not part of the radiation anymore. But I don't know what happens when eventually the black hole completely poofs, right? Then where did Sahil go?
mm. I see. I see. So, so there's actually an audience, a whole sequence of audience questions. I'll read them all to you, and then maybe from what we're discussing. Isn't there a balance between Hawking radiation will stop if there's no more space, meaning the entanglement in radiation is a cause and effect? Won't the cause stop the effect is not possible? Why should it keep going? See causality argument above.
Yeah, I mean you could propose that maybe Hawking radiation will stop when it's maximally entangled. But that means
Mhm.
that the quantum mechanics calculation at some point becomes wrong. That's a plausibility because we don't know, right? That's plausible.
Mm,
Yeah,
mm,
maybe I would say if space-time is really that benevolent, it doesn't want Sahil you to totally destroy yourself, then maybe it will try to preserve itself. But then at the same time, that means that black holes will never completely evaporate away. And that
mhm,
kind of is a little suspect, right? Because if you buy that the second laws of thermodynamics says that entropy always increase, and black hole evaporating is a very, very much thermodynamically favorable processes. So I would think that the black hole would very much like to evaporate. So my
mm.
money would be that the evaporation is somewhat unstoppable. I would think that. I mean, it could be
And
stopped.
so,
I don't
mm.
know, but my money would be on that it does not get stopped.
So okay, so if it keeps evaporating, um, and you eventually reach this point where this like firewall appears around the black hole, would you still see it evaporating, or like what? Because there's this barrier that like now is no longer like entangled with the space that you're in at the moment, or space time that you're in. So you wouldn't even see it radiate anymore, right? Or would you?
I mean, if you follow the error correction argument, then the
Mm,
firewall it's not all or nothing, right? Slowly, it becomes more and more messed up, basically the space time.
mm,
Slowly but surely, like so you can think of Hawking radiation as a little bit of error, you know, leaving the region of space. Slowly but surely, there's little glitches basically in the space time.
mm,
And at some point, when the glitches become super insurmountable, then it's a firewall. But
mm,
halfway, it's somewhere in between, right? Like I don't know, like maybe if I stick my hand in there, half of it will burn off, or I don't know. But there's gonna be an intermediate regime, but we don't really know what happens.
mm. And when you say burn off, you mean just like scrambled up and no longer, most likely no longer recoverable by you. It's not even like burned, because burning you could possibly recover back.
Yeah, it's
It's just
way worse than burn. It's like scrambled in a very unrecognizable way, and I don't even know how to quantify that. It's worse than a nuclear blast for sure.
oh, that yeah, this sounds highly unpleasant. I'm really glad that there's no firewalls here. Um,
Well,
at least for now, with my day-to-day life, I don't have to drive through a firewall to get to work. Yeah. So on that note, we're almost hitting time, so I wanted to give you a chance to, as part of our tradition, leave the audience any words of wisdoms that firewalls have taught you.
Yeah, I know that maybe this seems abstract. People say, "Oh, who cares? Black holes." Like we're not anywhere near a black hole. Um, well, the reality actually might be stranger than you think because remember, the universe is expanding, and the boundary of our observable universe is kind of like a horizon. So
Mhm.
Sahil, imagine you decided to take off, in a spaceship in some direction. At some point in the future, it could be that you hit a point of no return. So
Mhm.
in some sense, it's almost like we are kind of in a black hole,
Mhm.
right? It could be inside of a black hole, and maybe there is something like Hawking radiation happening outside. Of course, we can't perceive it,
Mhm.
and it really makes you wonder: what does it mean for us to exist here in this universe? Maybe all that is also temporary. Maybe our information will leak out some stranger places, right? Maybe we
Mhm.
are entangled to things outside of our universe with things that I don't know we can't control. I mean, I don't want to make it sound like supernatural or spooky or any way, but but maybe physics is even stranger than those supernatural thinkings, even stranger than that.
Um, uh, yeah, I buy that. Yeah, that is interesting. Maybe a future episode could be dedicated to like taking that even further. But yeah, on that note, I want to thank everybody for joining us, and we'll see you all next week.
Yeah, thank you all. See you.
Thank you.